This video is going to cover full structural models or full SEM and an example of how those work. So we're going to do both reflective and formative indicators in this one. So getting into a little bit of new code for Lavaan. So we're going to start with an example from chapter 9 from Klein, and it started as a CFA model with family of origin looking at the father side, the mother side, and a combination of the relatives, and then looking at marital adjustment, so problems with the marriage and intimacy issues. And so these are two very simple measurement models. And so we're going to start by building a full measurement model, just a CFA with a correlation between the two, and then change that to a directional path. So I'm going to start with my measurement model to make sure that runs, and then I'm going to change it to what would be a full model where I am predicting the direction. So this is a very simple full model, and then we'll do a more complicated one second. So for the example where the code is online, we have a correlation table. So we're going to import that data in correlation format, include the standard deviations, give it all names, and convert to covariance. So because we've talked about all of those several times, I'm not going to go over the code again. So if you can't quite get the code or you don't understand what some of that is doing, you should go back and watch some of the earlier videos on CFA where I cover that more in depth. All right, so in looking at this, let me load my two libraries. So I'm going to load in the correlation table. Right, so remember stacking it looks very nice, so I can tell it's correlations because there's ones on the diagonals. I'll load my standard deviations. And then I'm going to give it row names, column names, and name names. So the one for names has to be on the standard deviations. Now remember that the conversion from correlations to covariance is this core to cov function that's in Lavaan. And it's correlation table, comma, SDs. That's the way it works. Now, very specifically, we would prefer to use a covariance table so that we can see standardized and unstandardized solutions. But in this particular example, for some reason, this isn't going to work. And so I think it's a really good example of what might happen. To show you an error. So we haven't had too many errors so far this semester, which is good unless you've been working on assignments and you screw something up. But quite generally you're going to run into errors, so I've tried to find some that I know will blow up so that you can see what happens and to work on understanding troubleshooting those things. Alright, so let me go back here. The next thing we're going to do is build the measurement model. So just our CFAs with a covariance. And then we'll change it to full SEM. Okay? And when you do that, the loadings for the measurement portion should not change that much, because what's happening is you're redirecting the variance at the structural level, so the loadings at the lower level shouldn't change, maybe just a little. And we saw that when we did the hierarchical model, and so that's the video where I can't get degrees of freedom correct, but what you saw was that the loadings didn't change a whole bunch. The structural piece changed just a little bit because of some degrees of freedom moving around, but in general, the model looked about the same. If a full model is appropriate, meaning the correlation is there, and so you're just theorizing direction, this really won't change much. And in this particular model, that degrees of freedom won't change at all, except this one will get an error instead of a variance, right? But really, we're just changing this double-headed one to a straight one. So really, not a whole lot should change. But the difference between these two is really theoretical. So this one we're saying this predicts, it precedes it in time, predicts marital adjustment. Alright, well, where am I at? So here, let's see if this runs, and then on the very next slide it says it doesn't run. So just a warning. But when I built that model, I just did my normal CFA model. So adjustment is problems in intimacy, family is father-mother, and father-mother combination. So I'm going to try running that. And you'll see here that it says, well, it's grumpy about the fact that I used the word model here. I really shouldn't do that because model is a command in Lavaan. I should call it something else, but it got over it. here it says covariance matrix of the latent variables is not positive definite. And so what that means, if you remember way back when we talked about identification, is that the relationship between the latents is singular, is what it's saying. So it doesn't have a way to mathematically invert that matrix. Often the problem with that is multicollinearity, so the columns are too correlated. But these are latent variables, so I don't have a column to check, right? So there's problem number one. Or it just can't figure it out, in a sense. Often that's correlations or variances are very close to zero. So correlations too high, variances almost none. But it helpfully gives me something to figure out maybe what's the problem. Okay. So let's do that. So the code here is inspect. You take the fit of your model, so model fit here, comma, and then this literally. So down here it says the word fit. Well, what they mean is however you saved the fit a second ago, but this is a literal type. Okay, so I'm going to run that. So it gave me this covariance table, which isn't super helpful because it's in covariance. So you can also run this as core.lv, and that is where you'll see what the problem is. So when it tried to calculate the correlation between adjustment and family, and it came up with 1.06. And so that is a correlation over 1, so it's actually a Haywood case, and that is not proper, right? So it doesn't, it gives me a warning that something went wrong. Here's the trouble though. Often they will run and give you a summary. So you got to really pay attention when you're running these codes here. You'll see it here as well, this correlation that's too high. But all our variances are positive and all our R-squareds are less than 1. So we wouldn't maybe have noticed that. So when you're running these lines of code, sometimes, especially if you cut and paste them kind of quickly, it's easy to run your model fit real quick and then also run your summary and miss that warning in the middle. So always to kind of pause between those to make sure it doesn't warn you. Because the warning comes at the CFA line, not the summary line. It assumes that you saw that there was a problem and that you wanted to see the bad summary anyway. Okay. So it does run, it's just not correct. Because we have the correlation table, and none of these correlations are really so high that we should have gotten that sort of correlation. We do have some very, very correlated items. So father, mother, but those are on the same factor. So I would have expected them to be correlated. But I think the real problem comes in, we have this father, mother, and problems variable are pretty highly. That's 0.8, that's getting close to multicollinearity. And so that's one reason why that happened. So that doesn't really run. So I'm going to skip all of this here and just try it with the correlation table instead. Okay. So we're going to use the correlations to run this data just because it works a little better and it gives us an admissible solution. So now let's look at the summary. All my variances are positive, okay, and they are standardized already. So you'll see that the estimate and the standardized latent variable and these columns are all very close because we put in a correlation table. So that's one con to using correlation tables. My R-squareds are all less than 1. And then my correlation between these two items is much more reasonable at 0.6. Okay, so even though it gave me an answer for the last one, the solution was probably not appropriate. Okay. All right. So all of that looks good. Now I could go through up here and look at parameter estimates. So I stuck these in here because these are what we've been looking at. We could look at our fit indices, our modification indices, and we talked last week about sort dot equals, yeah, true to get them sorted. But if you look at this fit, it's really good. This model is not very complicated, and there's not a whole lot we could probably add. And so we've actually got some negative fit indices, which is sort of interesting. Sorry, that's the expected change. My fault. Here are the biggest fit changes. And those are really large. So it's wanting to cross and put father, mother on adjustment because of those super high correlations between that variable and intimacy, I think. And then it wants a correlated error here at father, mother. Okay. But if we look at the fit, let me use my summary here. Whoop. We should find this model fits pretty well, right? Because it's made up data. So our comparative fit index, oh, I lied to you, it's not good at all. 0.63, and our Tucker-Lewis is 0.71. Did I use the right one for that? Hold that thought. Fix the error, so let's go here. Okay, yeah, so actually the fits here is pretty terrible. I lied to you. Our RIMC is also really terrible. SRMR is not acceptable, but hey, everything loads pretty nicely. So, a good reason to stop and look at those. But this is an example for class, yay! So let's switch this over and use family to predict instead of just correlate. So what I did to change that, so if I come down, let's look at that picture, make sure I did that right. Okay. So one issue we're going to have is we only have 2 indicators on this one. That's not quite enough, but now I've got my full structural model. So what I've done is I've taken that measurement model here, and I've just added a directional arrow. So I'm saying family predicts adjustment, or adjustment is predicted by family. Okay. And let's run that. I stayed with the correlation table because I know that that at least gives me a admissible solution, even if it isn't a good solution. And what we should notice here is that these really shouldn't change, and they haven't a whole lot. Now fit is still pretty much the same terrible fit we saw earlier. So if I was to fix this model, I would have to work on fit first because all the loadings appear correct. They look pretty good. And what you'll notice here in the regression section, so this doesn't say covariance anymore, it says regression because we're predicting a direction. That completely standardized actually stayed the same. So it left that correlation there essentially, but you are predicting the direction. So that's why I say you really shouldn't see big changes when you go from the measurement model to the structural model. Now this is a very simple one because you shouldn't see these changes at the measurement level. You might see big changes at the prediction level, but not at the measurement level. Especially if you're sort of dropping, let's say you had 5 or 6 latents, and you let them covary at first, but then you went back and did all these different arrows. That is where you'll see changes hopefully at the structural level, but hopefully not too much at the measurement model level. Okay. Alright, so if I wanted to fix this model, what would I do? Okay, I don't really have this in the notes, because I forgot how bad this model was. But let's look at those modification indices one more time at this level now. So let's add sort dot equals true. And the first one is to cross list adjustment to or my father mother variable to adjustment. That's not normal, something you would do normally. Especially because we now have a directional path between those variables, so I expect that father-mother thing to actually predict adjustment. So I don't know that that's what I want to do, and so let's not try that one. Instead, being loud. All right. So instead, what I'm going to do is look at the second one. It says there's a correlated error between father and mother. Okay, and that is on a variable that has at least 3 indicators, so we can do this without too much trouble for identification. So what you can do is copy this exactly like this. I'm going to go up here to where my model is and add that in. Oops, no comma. Okay, just on its own line. So I'm going to run that. Run the model again, and it was really unhappy with me. So it says the covariance of the latent variables is not positive definite. It gave me some estimated variances are negative, so it did not like me doing that. Let's look at the summary here. So here's a Haywood case. The problem by adding that in is that it estimated a variance at a negative thing, which is no good, right? And so that didn't work. And one reason why it didn't work is this model's like really pretty much too simple. And so we could investigate why this is happening, but effectively it's thinking that the relationships between these things are not predictable is part of the problem. All right, so I'll leave that alone and end with this model is not very good. And I would have to maybe explore adding some more variables to help sort of make this model fit better. Okay. Now, we're going to try a more complicated model with some composite variables. Okay. So down here are two little mini CFAs with their measurement models. So I'm looking at achievement, which is a sum of the reading, math, and spelling. So it predicts those things. Classroom adjustment, so motivation, harmony, and stability. This is in chapter 10 of the Klein book. And then now I'm creating this risk variable. But I don't think they have some level of risk that causes socioeconomic status. I mean, maybe, but probably socioeconomic status is what's causing school risk. So lower socioeconomic statuses I would expect would be more risky in the classroom because maybe they're not getting enough food, their parents are never home because they're having to work several jobs, they don't live in a good neighborhood. So there's lots of reasons why that could create a risk for achievement in the classroom. Parental, psychiatric, and verbal IQ. So we're taking sort of three mildly unrelated things, like conceptually, and using those to create a composite of what we say might be risk for the classroom, right? And so we're going to turn those arrows the other way. This is a little unusual in psychology anyway, because we tend to focus here on this level of using latent variables that predict the output that we're seeing, but they are doable, and we'll talk about the code to how to do them now. So we have a correlation table, so we got to import that data, include the standard deviations if you have them, give it all names, convert to covariance, and this one runs okay. So it's a fairly big table because we have a lot of variables. So again, back to be sure you're stacking. Just makes life so much easier to see, right? Standard deviations, I've named rows, columns, and names. Okay. Now, you can name the names anything you'd like. Remember, no spaces. And convert to correlation, or covariance, sorry, covariance. So let me go back over here. So how do we define composite variables? We have not covered that yet. And in this particular model, we're just going to build the whole model at once to kind of just save time. But if the whole thing blew up, what I would tell you to do is start with the two little measurement models, then add the composite variable. Okay. So what we've been doing is equals tilde to define those latent variables that predict their manifest variables. Okay, we should be good at that at this point. To reverse the arrows, what you do is the little less than caret and then the tilde. The tilde represents estimate, so we're going to use tilde pretty much for everything, but the caret is basically turn that arrow around. Okay. And that'll create those composite variables that are predicted by its manifest variables, but it's still on the left here. So we're creating this latent. It is predicted by low SES, parental, psych, and verbal. It's very tempting to do low SES equals tilde and then risk, but Lavaan will be confused if you do that because it mainly expects the things on the left side with two little indicators here to be built, latents that you're building, whereas everything on the right tends to be manifest variables unless you're doing covariances or direct regression paths of variables that are already created. So don't do that. Tempting, but no. Okay. So this is going to create risk from these three, and then we're going to create achievement and adjustment from their own variables. So we're predicting out on those. And I almost think it would be better if it had the arrows of which way it was going. So it would be like tilde arrow. That would be a little much like conceptually beautiful and mentally beautiful, but it's not. And then we're going to use risk to predict achievement and adjustment. And so this one to me was a little tricky to understand why it was that direction, because I would think I could do, after I've built risk, I could do achieve tilde risk, adjustment tilde risk, right? Because those are already built and I'm regressing risk onto them here. But it actually turned out and worked better identification-wise if I sort of pretended that the risk piece here is a second order CFA. Because if you look at it, it is, right? So this is a second order CFA here, but it happens to be that the risk variable is created by something else. So for identification purposes, it was much, much easier to do it as this is a little mini second CFA. The degrees of freedom work the same, so it went okay. So let's run that. We're going to run the model, make sure nothing breaks. So down here, no warnings. Let's look at that summary. I think we're on like the second to last slide here. So we're going to run everything and look at all of the output that we should get. Sorry. So let's look at our fit indices. Compare CFI is acceptable. TLI is, should be better. Our RIMC is not totally acceptable, right? That's not in a good range. SRMR is good. So we got half and half, so mixed bag on these. And then it gave me my loadings here. So in looking at the loadings, for achievement by itself, they're really good. For adjustment, they're really good. And for risk, they're actually also good. So all my loadings are pretty strong if I use my kind of 0.3 criterion. But it's our composite variables that are kind of crap. So using low socioeconomic status and parental psych in this example do not help predict into risk, which risk then does predict quite nicely into achievement and adjustment. So it looks to me like this verbal IQ is actually what's predicting achievement and adjustment, and this risk thing is just kind of a waste of my time. So really what I should be doing is using verbal IQ by itself to predict achievement and adjustment, because adding in these two variables is not helping me very much, right? So they're non-significant, and they don't look like they're doing me a lot of good. All of our variances are positive. Okay? We don't have a variance on risk because it's a composite variable, and it is only predicting out. Let's see here. Our R-squareds are all really good too. I'm not predicting adjustment very well with risk, right? But I am predicting some of these other variables very well. Wrong button. Let's see. Let's look at our fitted. Let's actually just look at residuals. So with residuals here, we're getting some really big scores. So we haven't seen stuff quite this large. And these are still not standardized, so they're not necessarily the best. But it looks to me like most of the residuals are between the measurement pieces. So we're not predicting that part very well. And you won't actually get residuals in that area for composite variables. And then let's try modification indices. Maybe we can figure out what might fix this model. Scroll up here. So the highest thing I've got here is actually cross-loading a risk predicting spelling directly. So not quite what I want to do. Correlation between reading and math, which would make sense. A correlation between risk and achieve. Considering we were directly predicting achieve, I don't know if this makes a whole lot of sense. So a lot of these don't make sense. Maybe this reading math error correlation might help. So can't hurt to try that, so let's try it. Because they're on the same factor. Let's build a picture first. Make sure it looks right. So I got my 3 composite variables. So one thing you'll notice about composite variables when you blow up these pictures is there's no arrowheads on them. So the arrows are going into risk here. And that is because, I don't know, it just doesn't draw them. I don't actually know why. So let me come up here and add this. See what happens. Okay, and it gave me a warning. It did not like that. So this is probably not something I can get to run, because what happens is it gives me a negative area variance here for reading. Okay. So a lot of times modification indices will work. In these two examples it didn't really work because we're kind of at our limit for what we can do with the number of variables we have and the number of paths that we have, because remember, each piece has to be identified. So all that together is kind of sort of how you work with full sim using both reflexive and formative indicators.